Now we're going to do flat spacetime. So it's just like the analog of the Euclidean plane. And the only coordinates we're ever allowed to use are Lorentz or inertial frames, t, x, y, z. Right, so yes?
So does having a position vector acknowledge this vector define what a flat space is?
I guess you could do that. Be a kind of an awkward definition. Sort of say what you mean by this isomorphism and say a space is flat if and only if this isomorphism exists. You might be able to do that, yeah. We're going to define a notion of curvature, and we're going to say a space is flat if and only if it has zero curvature. But I think that does work, yeah. OK. All right, so let's get into it. All right, so we're not going to write little arrows, but we're going to say x mu is a Lorentz frame, or x prime mu, as we did. And the key thing about Lorentz frames is their transformation properties, right? So you can rotate and you're still in a Lorentz frame. You can boost and you're still in a Lorentz frame. You could also translate. You're still in a Lorentz frame. And we're most interested in thinking about the new one, which is the Lorentz boost. Okay? So remember that in a new frame, x mu prime, we introduced a matrix, lambda mu prime mu, x mu. So that was the Lorentz transformation law. Okay? And that is the hallmark of a vector. Okay? If you wanted to find the vectors by the isomorphism to the points in the plane, you can. You could also say a vector is something that obeys this transformation law. That would be an equivalent definition of a vector in the context of flat spacetime. Okay? So let me show you a vector right away. So you could regard these as a vector. I'm not going to use that because that won't generalize to curved spacetime. But remember, if you have a curve, x mu of lambda, some curve here, then we can make the analog of a velocity vector, dx mu, d lambda. But I haven't really decided whether the curve is time-like or space-like or what. So I'm just going to define this as t. And this is going to be the tangent vector. So that's like our prototypical example of a vector. If you give me a curve, at every point along it, you can take this thing, and you can define the tangent vector.
You mentioned we haven't defined if it's space-like or time-like.
Yeah.
Why does that matter?
I just wouldn't call it I wouldn't have a good name for it.
Oh, okay.
That's why I called it tangent vector, not like velocity. Yeah, it's always tangent. That's right. Thank you. Those are great clarifications. I really appreciate questions like that. OK. Now, I'm writing the components here. But abstractly, we want to do the same thing. We want to introduce this isomorphism. So just like you do in the flat plane, I'm now going to introduce the correspondence between points on the plane and unit vectors, which I'm now going to denote e lower Greek mu, that runs from 0, 1, 2, 3, like we talked about. And so these are our abstract vectors. This is our basis vectors, e hat mu. And so we could similarly write this tangent vector as t equals t mu e hat mu. Okay, and so that's why I put the mu downstairs. Yes, Hongji? No, this is the coordinate, and this is the vector. So this is the isomorphism. No, x mu is a coordinate. This is a coordinate on the flat spacetime. This is only possible to do in flat spacetime. This is how we're going to define the vectors in flat spacetime. We're going to pass beyond that when we get to curved spacetime. But we're going to get used to vectors and the associated new stuff, one-forms and tensors, in this context. Okay. So we have our abstract vector t. This is our abstract vector, which you'd think of as just living in the vector space. We have our canonical basis elements. So this is a particular basis associated with some Lorentz frame. Remember, we're in the universe where we're only allowed to consider Lorentz frames. So some Lorentz frame, and these are the components in that frame. Got to get faster at scrolling here. Components in the frame. Okay, and the point is, the whole idea is just as we sort of know that in the flat plane we could rotate our coordinate system and find the new components in the new basis, we can do the same thing here, right? So we can actually write it in some other frame. We could say, okay, alternatively, T mu prime, E hat mu prime, and this is just some other frame. Okay, so the abstract vector can be resolved into either of two frames. And now what we want to do is think about how the components change, because we might be interested in changing frames. Okay? And so from the transformation law for the coordinates themselves, we can figure out the transformation law for t, because we're just taking a derivative, right? And this is just another way of saying velocity vectors transform in the same way as position vectors in a flat space. Okay, so just from this equation here and this equation here, we can see that the tangent vector, let me scroll up so you can see that equation better. We can see that the tangent vector mu prime transforms according to the Lorentz transformation. Yeah?
So wait, are you saying that the components and the basis vectors transform in the same way, or do they transform
Oppositely.
They transform oppositely?
Yeah, we're going to see that in a second. I'm doing the components now because logically that's the way we're getting it first, because we already know how the coordinates transform. And now we can see, in order for this equation down here to hold, then we're going to need the basis vectors to transform oppositely. All right, so components transform with Lorentz. And we're going to see that it's going to be the inverse Lorentz transformation for the basis vectors. So how does that work? Well, let's do it. It's a little calculation. So we're going to use this equation up here that we wrote down. So in each case, right, we have T mu. So let's do this in another color, keep it a little cleaner. So let's take this, and actually, since we have the other one here, let's start with T mu prime. So let's take this equation here and plug it in. So this is going to be lambda mu prime mu T mu E hat mu prime. All right, I've just plugged in, hopefully. And on the left-hand side, we'll leave it as T mu E hat mu. Okay. And so you can see that for these to be equal, we're going to have to get a relationship between the tangent vectors, which is the basis vectors, which is E hat mu must equal lambda mu prime mu E hat mu prime. Now, if you notice, I just paused for a second there when I was talking. I doubted myself for a second. I was like, did I make a mistake? And the first thing I checked to see if I made a mistake is whether the indices line up, okay? So every equation should have the same number of free indices on each side, not summed over, and they should be in the same upstairs-downstairs position. So good, I have one downstairs mu and one downstairs mu, so that's working. And any summed indices should have one up, one down. Good, I have one upstairs mu prime and one downstairs mu prime. Okay, so that's what I did there to pause to check myself, look good, move on. You want to do this in your homework all the time. Okay? Check every step whether all the indices line up. Because if you get to step 50 and the indices don't line up, now you have to check all the way back to find your mistake. All right? So this is a terrific way the notation can help you catch mistakes. Yeah?
The different classes where one with lambda, like the index and the left placement is for your new frame, and the right is for the old frame. Are we using that rule in this class?
It is if you make prime the old frame, the new frame. I don't know. I'm using prime and unprimed. Okay, so this is a transformation law. Now, I mean, maybe what you're getting at, and I might as well learn names. I know you told me, but tell me again. Rudy. Okay, Rudy, Wolfgang, Evan, Hongji, Vivian. All right, very good. Okay, but then this does say, give you the unprimed frame, and if we want it to look like the primed frame, an equation for the primed frame, what we better do is invert this to solve for e mu prime. Okay. So how do we invert this? Well, if you think of this as a matrix multiplication, you can imagine we need to multiply by the inverse matrix. Or if we just think about Lorentz transformations, we will realize that if you Lorentz transform one way and you Lorentz transform the other way, which is the same as reversing the velocity, then you get back to the identity. So Lorentz transformations are going to obey an equation that says lambda mu prime mu, lambda mu nu prime is delta mu prime nu prime. Now, I'm not sure if I lined the primes up for how we need them, but we'll get there. Okay, so we'll call this the Lorentz transformation based on the convention that this is what we mean by going forward from unprime to prime. And then this matrix, by definition, is inverse Lorentz. Going backwards, because this is a matrix multiplication, multiplying, giving you the identity matrix. So in case you've never seen this before, Kronecker delta is just 1 when mu equals nu and 0 when mu not equal to nu. So it's an index way of writing the identity matrix. And the inverse Lorentz transform you can check by inverting it, or just physically it's the same as transforming with v goes to minus v, right? Because you change the velocity going one direction. If you want to invert, you just boost in the other direction. Okay, so we have that equation, and so what we can do is put it in here, and hopefully I did it right. Let's see. If we multiply both sides, e hat mu lambda mu nu prime equals lambda mu prime mu e hat mu prime lambda mu nu prime. So I just multiplied both sides by this matrix and then by this equation. This is just lambda mu prime mu. I plug in here delta. Uh-oh, I've got a messed up index. I'm okay. This is mu.
Yeah, it's just going to be delta mu prime.
But I've got an up mu prime.
That is part of what cancels into the delta.
So that's what I messed up. See, you can always catch your mistakes if you're checking index all the time, right? Very good. So let's bring the e hat mu prime here, and then this just becomes delta mu prime nu prime using the equation. Okay? And this is something you get very good at as you do index notation. You remember there's a sum over mu prime here. Delta is only non-zero when mu prime equals nu prime. So I might as well set mu prime equals nu prime. And so all I get is e nu prime. Okay? And now I've derived the transformation law for the basis components, the basis vectors. The new basis vectors, e nu prime, are given by the old ones, e mu times this inverse Lorentz transformation. Yes?
Is there any reason why you put the index in parentheses for the vectors?
Just to keep track, because the non-parentheses index refers to coordinate components, and the parentheses index refers to which abstract basis vector you choose. So they're mathematically different objects, and that distinction becomes more important in curve spacetime. And we'll actually have a totally different notation for this E hat in curve spacetime.
Just as a double check, because I think it's safe, but down here we're writing the Lorentz transform on the right side instead of the left side of the E vector, whereas earlier I think
Right, so here,
on the left, since it's tensor notation, that's entirely fine.
right, these are literally numbers.
Right.
This is,
You're just like scalars at this point.
these
So
are the components of the matrix, yeah.
once you go to actually evaluate it, like how we tend to have the inverse Lorentz transform on the right instead of the left in this definition.
When I rewrite it, I'm gonna put it on the left. So up here, I'm gonna add to, but it doesn't matter. It really doesn't.
Yeah, I was just doing it.
And that's one major advantage, in fact, of this component notation over matrix notation. You don't have to worry so much. Yeah, exactly. Okay, so let's reorganize things a little bit. Put that down there. And now put our result we derived. So E hat sub mu transforms according to the inverse transformation, and it's sort of the only way it could be with the notation. Oops, that must be mu prime, mu E hat mu. Wait, that's the same. What have I, oh, I'm trying to get mu prime. Very good. Okay. So I'm trying to get mu prime, so the prime has to go down here. E hat mu, and so this is now the inverse. So the vectors, the basis vectors, transform with the inverse Lorentz. Okay, so that's something to keep track of, difference between the two. And I present this mainly for logical completeness because as we get into this, we're almost always just going to work with the coordinate components. But, you know, we want to keep track. There's an idea of an abstract vector in abstract vector space. You change the basis by the inverse Lorentz transformation. The component is changed by the Lorentz transformation. The abstract vector is invariant, which is the same thing as with rotations, right? If you imagine taking a vector and changing the basis, you know, you could rotate the basis like this, and then the effective components of the vector would be as if, you know, things had gone the other way. Okay, any questions? Mm-hmm.
When we're talking about like the components changing, why do we, I guess you said we don't really use it, but like this notion that we have this basis vector and it changes in the reverse way and that maintains its variance is good, but like if we know how the components change, do we even need to care about what the basis is?
If you just want to calculate, no. But it helps to understand how all these things are constructed. I mean, those are the components in that basis. So you may have to tell someone someday that your calculation refers to the following basis, and you know. Okay. All right, so that introduces a bunch of notation for something that really should be totally familiar from vectors in the plane or in three-dimensional space.